composite reliability and average variance extracted. So I will now demonstrate how composite reliability and average variance extracted is computed. So to do that, remember we were talking about that we will be using standardized factor loadings in order to compute that. So this is the standardized regression weight. So we will copy this output and you can have go to your a blank Excel sheet and just paste these values, right? So this is the value that we have got from the AMOS output, right? So this is the AMOS table, standardized regression weight. We have pasted it in the Excel sheet. Now this estimate that we have here is nothing but the lambda, right? If I were to uh, remind you of what we were doing, right? So we had said composite reliability. This was our formula, right? So we had said composite reliability summation lambda I whole square divided by summation lambda I square plus summation 1 minus lambda I square, and where lambda I we had written as standardized factor loading. Similarly, what we had also done was we had written a formula for average variance extracted, and we had said it is summation lambda I square. So we will square the lambdas and take the sum and then divide it by the number of items, which is k. So the same thing is what we are going to do now here in our Excel sheet. I told you that this is the lambda, okay, the loadings that we have computed. And we will now start working on this sheet. So we will get lambda square, right? So we want to compute lambda square now. So we have lambda, we will compute lambda square. And then we will also compute 1 minus lambda square. Okay, so we have got now lambda square and 1 minus lambda square. So what is lambda square? It is nothing but lambda multiplied with lambda. E6 multiplied with E6, that is lambda square. And then you pull down this formula to all the cells in your Excel sheet. Right, so this is nothing but very simple Excel computation. We are just multiplying 0.812 with 0.812, E6 with E6, E7, and so on. Then 1 minus lambda square, so 1 minus the lambda square, 1 minus F6. This becomes your 1 minus lambda square, and then you pull this formula in all the cells that we are. Then we will also need for each factor. Okay, so let me introduce a row here. This was EMP, then we had LEA, TO, and LEA. So we have the three factors. This is EMP, this is task orientation, and this is lead-in by example. So now we will also compute for this factor completely, we will compute sum of lambda, right? So what is sum of lambda? It is the sum of the loadings for this factor. So we needed for composite reliability, we need sum of lambda, right? Remember this formula, we said sum of, for composite reliability, we had said we will take the sum of the lambdas. So this is the, this part is, this part is sum of lambda that we are computing, right? So this is sum of lambda. So we are now going to go there and so let me share my screen again and go to the Excel sheet. So we have sum of lambda here. So this is for one factor. Similarly, for task orientation, it is going to be sum of these lambdas. And then for LEX, it is going to be again sum of these three lambdas. Okay, so this is got some lambda. So what is, and let us also compute sum of 1 minus lambda square. Okay, so we'll compute the sum of 1 minus lambda squares. So which is nothing but the 1 minus lambda square is similarly sum of these four 1 minus lambda squares and then sum of these three lambda squares. So let us again center it. Okay, and now what is composite reliability? Composite reliability is nothing but square. So let me write this as, just to make it simpler, you will also take square of some lambdas. Okay, so that we don't confuse. So this is the square of the sum of lambdas that we have computed. Similarly, for this, it is going to be square of this number that we have computed, and this is going to be square of this that we have. Right, so we'll again center it. Right, so we have now got this square of some lambdas and sum of 1 minus lambda square. So what is composite reliability? Composite reliability is, if you look at your formulas, square of some lambda, so sum of lambda whole square divided by sum of lambda whole square plus sum of 1 minus lambda square. Right, so this becomes your composite reliability for E and B. Similarly, we will compute composite reliability for task orientation. So sum of lambda whole square, then divided by sum of lambda whole square plus sum of 1 minus lambda. Right, so it becomes 0.89. And then for the third construct again becomes sum of lambda whole square divided by sum of lambda plus sum of 1 minus lambda. Right, so we have now got our composite reliability for the three factors, and we had said yesterday that the composite reliability should be greater than 0.70, and we are getting good composite reliability for the three factors. So this shows that after accounting for measurement errors also, the inter-item consistency is quite good, and the latent factor is sort of the true factor variance is at least 70% of the total variance in the data.